All right, boys and girls, another lecture here. Today we're learning about determinants, trace, and inverses. Super easy lecture today. More on matrices, of course. We're on the matrix theme. So first, let's talk a little bit about determinants. So determinants are really a way of assigning a number to each matrix. You could think about it in a fancy way. The determinant could be a function from square matrices, n by n, in some field A, and they get mapped to A. So, in other words, the input is a matrix, a square matrix, by the way, and the output is an actual number, or it could be a polynomial, or it could be a complex number. Whatever the field A is, that's what you're going to get out of it. So you start off with a table and you assign it an actual number value that's not necessarily a table. Okay, that's a determinant. So the easiest way to start is with the smallest square matrices. Those would be 1 by 1. So say that the matrix A is just a 5. In that case, the determinant of A is simply just the number 5. Okay, that's like the easiest thing in the world. Might be a good time to introduce notation. Another way of saying the determinant, let me write it better. Another way of saying determinant of A is also to say A with an absolute value sign like this. It should remind you of absolute value. But when the thing inside is a matrix, then by context, this is not interpreted as absolute value. It's interpreted as determinant. Okay. Also, a lot of times people will use those straight brackets here rather than the ones that have this. This is the matrix. That would be the determinant of the matrix. Yeah. So for 1 by 1, it's the simplest thing in the world. All you do is take the number, whatever it may be. So the determinant of -8 would just be -8. That's it. End of story. Now let's make it a bit more interesting and consider 2 by 2s. So suppose you have A is equal to a 2 by 2 matrix. 1, 2, 3, 4. Yeah. The determinant of A, again, just so we can get used to the notation, could also be written as determinant of A, or it could also be written as 1, 2, 3, 4 with these absolute value signs like this. Again, if they were regular numbers, it'd be absolute values. In the context of matrices, it's determinant. Okay, these are 3 different ways to write determinant of A. And the way we're going to define it for 2 by 2 will be to take the product of the diagonals this way, we'll multiply the 1 and the 4, and then take this product, the opposite diagonal, 2 times 3, and then subtract them. So the determinant of this particular matrix would be equal to 1 times 4 minus 3 times 2, given of course 2 minus 6. Okay, that's how we calculate the determinant of a 2 by 2 matrix. One more example and then we'll move on. What if you wanted to find the determinant of -1, 3, -2, 1? I don't know, something like this. So this would be, again, we're going to take the diagonal this way and multiply them. And then we're going to take the diagonal this way and multiply it and subtract this one from this one. So that will give us -1 times 1 minus 3 times -2. Of course, giving us a grand total of 5. Okay? That's how you calculate determinants of 2 by 2 matrices. Now the 3 by 3s get a little bit more interesting, so let's actually go forward, and I think I have some examples set up for us on the next page. Oh yeah, the cofactors. So let me come back to, let's talk about cofactor. So the cofactor of every one of these guys, 1, 2, 3, every one of these has what we call a cofactor. and they're based on the position. So this is the 1, 1 position, this is the 1, 2 position, 1, 3, etc. So suppose you wanted to find the cofactor for the position 2, 3. So second row, third column, that's 2, 3 right there. So the way we do it is, if you want to find the cofactor of this, it's actually going to be a number, and I'll show you how to cook up that number. First thing you do is you block out the row and you block out the column. By blocking out the row and the column, that gives you a submatrix. I'm looking at the submatrix right there, 2, 3, 5, 2. And what you do with that submatrix is take the determinant of it. Take the determinant, and then you assign to it a number. You multiply by either 1 or -1. And I'll show you how to determine how to multiply by. So first thing we do is so let me just write the steps real quickly so that it's super clear. First thing we're going to do is block out row and column. So let's do that real quickly. Block out the row, block out the column. Okay, second step we do is compute the determinant of the submatrix. So in this case, it'll be the determinant of 2, 3, 5, 2. That will give us 2 times 2 minus 3 times 5. Of course, that's equal to 4. That will give us the determinant of the submatrix. Third thing you do is multiply by -1 raised to the, in this case, 2 plus 3. Okay? 2 plus 3. You take these, the indices, 2 and 3, and you add them. That gives you 5. And since 5 is an odd number, you're going to multiply by a -1 raised to an odd number is going to give you -1. And so finally we have the cofactor for the position 2, 3 would be equal to -1 to the 5 times -11. We're multiplying that special sign, whether it's positive or negative, times the previously computed determinant of the submatrix. Grand total here is going to be 11. And that's how we compute the cofactor of any one of the entries on our matrix here. Okay? So let's do one more example of a cofactor. I meant to put a different one here, something like maybe 3, 3. Okay? We're going to compute the cofactor for A33. So it's going to go like this. We're going to try to follow this recipe. We're going to block out row and column. Let's do that first. So 3, 3 spot is this spot right here. So we block out 3, 3 position. Then we compute the determinant of the submatrix. So the second step here would be the determinant of 2, 3, -1, 4. That would be equal to 8 minus -3. That's 11. And then the third step here, multiply by -1. This is steps 1, 2, 3 already. -1 raised to the 3 plus 3. So that's what happens is that's an even number. So that's going to be a 1. That's an even position. So this last step is not going to be any, it's not going to change the 11 at all, because 11 times 1 is still 11. So that's going to leave us with the following statement. The cofactor for the position 3, 3 is equal to 1 times 11. Okay. There's an easier way to see this little business about changing the sign or multiplying by negative to some power. What's going to happen is all of these ones. So this is the 1, 1 position. That's even, so that's going to be a plus. This position would be the 1, 2 position, row 1, column 2. If you add 1 plus 2, that's 3. That's going to be odd, so that's going to end up changing the sign. The next one, this one will be 1, 3, row 1, column 3. That's going to give you 4. So that would be 1, negative 1 to the 4th. That's going to be an even number, so that's not going to change it. And so you see, eventually you see that all you got to do is just think about this checkered pattern. That's exactly how you will know whether or not you need to multiply by negative 1 or not. Or you can just always just, if you're more, if you like formulas better than visual things, you might want to just stick to this. Add these two indices together, and that's the power that you use. And if it's an even, you know you don't have to change the sign. If it's an odd, you do. All right, that's the cofactor story. Now, I explained the cofactor story because it has a lot of implications. But among other things, it has it also helps us figure out the determinant of the 3x3 matrices. Determinants of 1x1 matrices we already did earlier. 1x1 are super easy. All you do is just take the number. 2x2 is super easy. All you do is multiply the diagonals, subtract them. The first diagonal minus the second diagonal. So we didn't get to 3x3 matrices, but the 3x3 matrices will make use of this cofactor idea in a very neat way. So let's do a 3x3 matrix or for a determinant. Again, for 2x2 is super easy. All you do is take this minus that. So in this case, it would be equal to 2 times 4 minus negative 1 times 3. And then you're done. Okay? Again, all you do is do the 2 times 4. 2 times the 4 minus... Was that the same one? That's the same one. Wow. Okay, so let's move on to a 3x3. So for a 3x3, what we're going to do is we're going to use a technique called expanding by minors. And it turns out that you can expand by minors along any one of the rows. So you could do it this way, expand by minors along this row, or that row. Or you can expand by minors along any column, this column, that column, or that column. Okay? So you have 6 options. Any one of them will lead you to exactly the same answer, the determinant. Let's just keep it simple. Let's say, first step, pick a column or pick a row. Any one row or any one column. Usually, it's to your advantage to pick one that has zeros in it, because then you know, because you'll see why, because it makes the computation easier. So, any one of those would be good. But let's not go for easy. Let's go for thorough understanding at the moment. First step is choose a row or choose a column. Okay? Just one. Any one row or any one column. So let's say I choose this one. Okay? Done. Second step is I want to expand by minors. So that means that I'm going to have 2 times determinant of some stuff plus 3 times determinant of some stuff plus 1 times determinant of some stuff. And the stuff that's going to go here will be the submatrix that you get when you cross out row and column. The one that you get here will be this submatrix that you get when you cross out row and column. And the one that you put here under the 1 would be the submatrix that you get when you cross our own column. Exactly the same as when we just got done doing with the cofactors. That's why it's good to talk about the cofactors before we talk about this 3x3 determinants. Okay? Now, so let's just do it. For the first one, for the 2, here's the 2. I cross our row and column, and that's going to give me a submatrix. So I write that submatrix down. So this will be 4, 0, 2, negative 3. Then for the 3, I cross our row and column, and that's going to give me a submatrix. Submatrix will be negative 1, 0, 5, and 3. So you got your negative 1, 0, 5, and 3. Like this. And of course, the last one, we're going to cross our row and column. That's going to give me a submatrix. That's going to give me negative 1, 4, 5, 2. The third step, important step, is multiply each of these by -1 to the I plus j, where I plus j is the index. Okay? I is equal to the row, j is equal to the column. Okay? In other words, the exact same thing that we did before with the signs. So this one, the first one, here's our 2. That's our 2. That's row 1, column 1. So since that's row 1, column 1, this would be multiplied by 1 to the 2. So it's really -1 to the 2, so nothing happens to that. Or if you want to be pedantic about it, we can do here. This one gets multiplied by -1 to the 2. This one gets multiplied by -1 to the 3. This one gets multiplied by -1 to the 4th. So really, these guys don't matter. The only one that gets changed to sign is this one. Or you could see it differently. You have a plus here, you have minus here, you have a plus here. So the only one that gets a sign change would be this one. These do not get a change of sign. Only this one does. And so finally, you just compute it. So let's go ahead and compute it. This will be equal to 4. And I know you guys might have seen other tricks where you write this matrix over here and then you do these columns minus those, whatever. I don't want to take shortcuts right now. This is super important. It's a really good way to doing it, using expansion by minus along any row or column, because it has other deeper implications. So if you've seen other ways of doing it and you think that those are better, just hold that thought for a little bit, because we're going to use this for other things. Okay, so all right, so I got 2 times, well, this would be 12 and then a 0, so I'm going to go like this. Okay, and here I have a -3 now, because I already incorporated the change of sign on that 3. And then I'm going to do this one, this minus that. So that's going to be 3 minus 0. Okay, and then I'm going to have a 1 times, and then I'm going to do this one, -2, and a 20. Okay, so it gives me -2 minus 20. That's it. You add that up, and you get whatever. You got -24 plus 9 plus -22. Okay, that's your last step. And it's interesting to know that no matter which way oh, by the way, you have to compute that. It's interesting to note that no matter which column you had expanded by, say you had expanded by this column instead, you would get the exact same number. Say you had expanded by this column or this row, you would have gotten the same number, or any one of the columns. In fact, that's a really good proof to do if you want the challenge. Prove why the determinant turns out to be the same no matter which row or column you expand by. Okay, so that's our talk on determinants. Might be fun just to try it. Expand. So let's just do it for fun on a different expansion, and I'll explain another thing too. Remember I told you that sometimes you might want to expand along rows that have a bunch of zeros, or as many zeros as possible. Let me show you why. So this one, let's just do this one more quickly. So it'll be 1 times some submatrix plus 0 times some submatrix plus -3 times some submatrix. Now I'm going to try to check my signs here. So let's go with red for the signs. This is plus, this is minus, this is plus. So this is plus, this is minus, this is plus. So I'm not changing those signs. Now take care of the submatrices. This one is If I cross out row and column, that gives me this submatrix. So that's going to be... All right, so once we have our cofactor set up and we have our signs here, we're going to start with our submatrices. For the first one, for 1, I'm going to block out row and column. I'm going to pick out that submatrix. So that submatrix is -1, 4, 5, 2. For the next one, I'm going to block out that row, that column, and that row, and I'll pick up that submatrix. So it'll give me 2, 3, 5, 2. And by the way, this is why we love zeros, because who cares what this is? This is going to be multiplied by 0 anyways. So that's all going to go away. That's why you want to pick rows or columns that have a bunch of zeros on them. Because this one, who cares? All right, for the 3, we're going to block out this row and this column, and that will give us that submatrix. That's the one that submatrix is. This is the one that needs to go here. So we will have 2, 3, -1, 4. And then we just finish the computation. This will be 1 times -2 minus 20 plus 0 times, who cares, plus -3 times 8 minus -3. So that's going to give me -22 plus 0 plus -3 times 11, -22 plus -33, -55. Now, just for fun, you should be able to match that over here where we did before. These two give me 46, and then a -9, that gives me -56. One is -55. So it's interesting to note that no matter which row or which of the column, you got 6 choices. They all lead you to the same determinant. Okay, that's how you do 3x3s. Now, not only that, but that also tells you how to do 5x5s or 4x4s or anything. All you're going to do is pick a row or pick a column, just like these steps show you. That's why this is much more beautiful than that other trick that you might have seen in other classes where you do this. This is really expandable to any size matrix. You're going to still choose a row or column. You're going to expand by minors by blocking out, a row and a column, and that gives you a submatrix. If this was a 4x4, the submatrix would be a 3x3. If this was a 10x10, the submatrix would be a 9x9. And so you could go on and find the determinants based on the techniques for finding determinants of smaller square-by-square matrices. Expand by minors, make sure you add the right signs to it, and just crank it all out. It's beautiful. This is consistent. It always works. All right. That's how you do determinants. Look at this. Talking about a bigger one. How would you do this one? Pick a row or a column, and then you could do it. Because this one has a lot of zeros on the bottom, it might be a good idea to pick the one on the bottom. I'll just go through the steps real quickly, just for fun. I'm not going to do it because it might be kind of boring. But let's just go through the setup. The setup might be instructive. So once we got the row, we start our expansion. So this will be 0 times some stuff plus 1 times some stuff plus 0 times some stuff plus -2 times some stuff. Okay. Then I add the signs. I'm going to use my checkered board technique. So this is plus, minus, plus, minus. So this one changes signs. This one stays alone. That one changes signs. That one stays alone. So that gives me the right signs. This one would change sign, and this one would change signs. So of course, in this case, I'm lucky because it's 0. So who cares? That's going to go away. Now for the 1 here, I'm going to be careful and cross out row and column. So I'm going to cross out, for the 1, I'm going to cross out this row and that column. And that's going to give me a submatrix. The matrix that I get would be 2. The submatrix that I get would be a 2, a 1, and a -3. A -1, a 0, a 1, a 5, a -3, and a 2. Okay? I'm looking at this submatrix here, the one that's left over. 2, 1, -3, 2, 1, -3, etc., etc. All right, the next one I need, the last one is the submatrix for the -2. So for that, I'm going to clean this up a little bit. And then I'm going to show that I'm expanding by minors along the last row. I'm going to cross out this row and that column. And that leaves a submatrix. That's the submatrix I want to pick up. So it'll be a 2, 3, 1, -1, 4, 0, 5, 2, -3. And so what we've done is we've reduced the 4x4 matrix into a couple 3x3 the 4x4 determinant into a couple 3x3 determinants. Okay, still not the most fun thing in the world, but it's kind of easy. So that gives you the story on determinants. Okay, tells you what a cofactor is, how to do 2x2 determinants, how to do 3x3, how to do these ones. Maybe we should say a couple things about determinants. It's interesting to know that the determinant of the product of two matrices is equal to the product of the two determinants. Whoa, I know. And of course that allows you to figure out the determinant of the inverse of a matrix. Here's a little cute proof on how to figure out this determinant. So here you go. A times the inverse of A, of course, have to be the identity. The identity meaning the matrix that has ones on the diagonal and zeros everywhere else. That would be the 3x3 version of it, for example, but it could be any n by n. 4x4, 5x5, whatever. So now, if this is the case, I could slap determinant on both sides and say, okay, I'm going to slap determinant on this side and determinant of that side. Now, I'm going to use this fact right here that I can break up the determinant of a product into a couple of different determinants, the product of the determinants. So this tells me that the determinant of A times, let me keep it blue, sorry. Determinant of A times determinant of A inverse must be equal to determinant of I. That's using that previous property. Now I also know the determinant of I. If you just have a diagonal like this, the determinant will just be 1. Because you can have a 1 and then all this breaks down to submatrix. These are all zeros, so you have this and that's a 1 and that's a 1. So it ends up being 1. This is a super easy determinant to compute. And so I get that the determinant of A times the determinant of A inverse is equal to 1. So that tells me that the determinant of the inverse of the matrix is equal to 1 divided by determinant of the original matrix. All right, and that tells me other things too. Suppose the determinant of A was equal to 0. That would mean that the other determinant is 1 over 0. That's not even a real number. So it already tells you that in order to even hope for an inverse to exist, the original matrix has to have a non-zero determinant. So there's the first use of determinants. It tells you whether or not you even have hope of finding an inverse of a matrix. Not all matrices have multiplicative inverses, by the way. Okay, so there's a cute little proof of the fact that, let's circle it, the fact that the determinant of a matrix, determinant of the inverse of a matrix is the 1 over the determinant of the matrix. Okay, all right, I think that's good for one day. I'll post some more lectures soon. We'll see you guys here on the next one.